All right, let's try and write our own basic hash function, for now just with strings. So the goal is to write a function, let's just say it's called hash, and we pass in a string like, I don't know, pink. But on top of that, we also pass in a length of an array. So if we're trying to store our hash table in an array that is 100 items long, we would pass in 100. So this will map pink to be a number between 0 and 99, a valid index in that array. If we did pink, 9, this is hopefully should give us a number between 0 and 8 so that we can store it in the array in a valid position. So to write this, let's ignore this last thing to start. How would we just convert pink to a number? There's many ways, but remember it needs to be reliable, deterministic, meaning that it is reproducible every time we get the same output. So we could just take the length of pink and just call it a day and just use 4. The problem with that is that a lot of strings have the exact same length. So if we're working with, the English dictionary and we're trying to store words, I don't know what the most common length is, but they're definitely small strings, traditional words. They're not very long. So we're going to have very clustered data. If we had an array that was 1,000 character or 1,000 positions long, they'd all be less than, I don't know what the longest word in English is, but they're all less than 50 characters probably. And most of them are less than 10 characters. So that's not really great. But there's another thing we can do, which is to use the underlying UTF-16 character codes for each character. So every character has a numeric value associated with it. And you can actually access that. Like if we do A, there's a method called char code at or car character code at. And we have to pass in an index like 0. And that corresponds to the 0 index of this string. There's only one character. And it gives us a number. Or if I had hi and I did 0, it's going to give me the number for h. If I did it for 1, it gives me the number for I. So these numbers we could basically add them together for a given string. Also, to make it a little simpler, if you subtract 96, this will give us the alphabetic ranking or position. So for example, A is now 1. If we did D, it should be 4. And if we did Z, that should be 26. Perfect. So that works. It gives us, the position in the alphabet, starting from 1 up to 26. So we can use this, and on top of that, we'll add them together. So we'll continue to do this for every character in a string. So let's say I have a variable called total to store everything in, and then we're working with the string hello. So we would do total plus equals the character at position 0, so car code at 0, and then we'll subtract 96 so that this is just to make it easier for us. You don't have to subtract 96, it's still valid. So that adds 8. Then we're going to do character code 1. So that's for E. We do this in a loop, of course. This is for L. This is for the other L. Then we get to O, right? Is that it? 1, 2, 3, 4, 5. Yes. So that's our total value in there. So we get 52. But then we also need to consider that we talked about calling our hash function like this, where you'd pass in a string and then a length. Let's say 11 is our length of our array. We need an index that is going to be valid, and 52 is not. It's too large. So how do we keep it within these bounds? The simplest way is to use modulo. If you don't know or don't remember modulo, it's the % operator in JavaScript and in pretty much every language, programming language at least. Think of it as, you divide something by a certain number and then you take the remainder. That's what we store. That's what we return. So 13 mod 3, for example, 3 goes into 13 how many times evenly? 4 times, right? 4 times 3 is 12. The remainder is 1. We have 1 left over. So if we take the length of the array that we're trying to store, if I say 11, we take total, which is 52, and I modulo, or mod, 11, we end up with a number that is valid to store our data in, which is 8. So whatever the number was, we could take a giant number like this. If I mod by 11, we're going to get a valid array index now between 0 and 10. Just to prove that one more time, keep adding something. You can see we're getting these numbers that are valid array indices. So I have the function already written in the slide. Here we go. It looks like this. Function hash, it takes a key like pink, an array length like 10, and then we make a total variable. We loop through the characters in the key, P, and then I, then N, then K, and then we add the character code for each character to that total. And actually, the way that I decided to do it here is to use the mod array length as we build the string, as we total up the string. So instead of doing a mod at the very end, we add each thing in, we modulus by the array length, and then we start over. Again, the way the hash function works is not the focus here, but I just wanted to show you this is a basic hash function. It's not perfect, but if we called hash with pink and we want to index less than 10, this one gives us 0. We do it with orange red, we get 7. We do it with cyan, we get 3. So it appears to work. I do have it over here as well. If we run it, let's call hash on pink just to make sure. And we will call 10 so that we get an index between 0 and 9. I always get 0 no matter what. If I quit my browser, I restart it, I'm always going to get 0 when I call pink with 10. Now, if I did, let's do I don't know, orange, I also get 0. So that's something we have to consider. We'll evaluate whether this is a good or bad one in just a moment. Let's try blue. 0 also, no. How about cyan? Okay, so we get 3. How about purple? We get 8. And maroon? All right, so you see we do get these numbers and they're all less than 10. So that works, and every time I call it, I get the exact same output. According to the rules that I laid out in the last video, there are a couple of problems with this current hash function. First, we're going to ignore this one, but it only hashes strings, right? If you tried to give it a number or a Boolean value or something like an array, it's not going to work because we're using a string method. So that's a problem in general if we're trying to actually implement something legitimate. But we're not going to worry about that because that's beyond the scope of this. We're only caring about strings. But a bigger problem is that it's not constant time. The time that it takes, the number of operations that we do, depends on the length of the string or the size of the data. So if we pass in a larger string, it takes longer to hash it. It scales along with the size of the input. So that's not good. We want to fix that. And also, this one's important. It's not very random. Our data can be clustered relatively easily. And so we're going to talk about in the next video ways of improving number 2 and 3 here. Of course, we're going to end up with clustered data when we're working with numbers, between 0 and 10. There's only 10 options for our values. So of course, we're going to have some duplicates, but still, this is not perfect. There's ways of making it slightly more scattered. And I'll give you a hint. It involves using our friend, the prime numbers. Our friends, the prime numbers. Okay, so in the next video, we'll improve this so that we don't end up with this loop, so that we can have a constant time for our time complexity, and then also add some prime numbers in to make this a little more random or distributed evenly.